Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. My name is Wahyudi, and my partner Mustafa, Kosyanto, Andri Kurniawan, Lasriah Manurung, and Gita Puspitasari. And we are from Department of Chemical Engineering, Politeknik Negeri Samarinda, Indonesia. Today, we would like to make presentation. I would like to invite my partner Gita Puspitasari.
Thank you, Mr. Wahyudi, and thank you, Borobudur International Symposium 2025, for this opportunity. I would like to present our research with title Utilization of ironwood sawdust waste as an adsorbent through chemical and physical activation processes with various KOH activation concentrations. This our contents. First, introduction. Second is research methods. Three is research results and discussion. And the last is conclusion. As wood production increases, the sawdust pile continues to grow. Fortunately, woolen wood or ironwood sawdust is about 60% cellulose, and this high content makes it an excellent research for creating activated charcoal, which make it great for absorption. Therefore, this study was conducted using variations in KOH concentration on the quality of wood sawdust activated charcoal as an adsorbent. First, we need to prepare our materials. The main material that we use is woolen wood sawdust or ironwood sawdust. The pretreatment process for the sawdust involves reducing its size and thoroughly cleaning it, because when we receive or we got the ironwood sawdust from the industry, it's not cleaned yet, so we need to wash it and then we have to dry it in the sun for about 3 days. The next step we need to do is carbonization process. We need to carbonizing ironwood sawdust with a furnace at a temperature of 500 degrees Celsius for about 1 hour. We choose this condition because it's generally effective and efficient. After the carbonization process complete, next we need to cool ironwood sawdust charcoal into a desiccator for approximately 15 minutes. While we doing a carbonization process, we also we also prepare an activator solution with varying concentrations from 3%, 5%, 10%, 15%, and 20%. The activator solution was prepared by weighing 3 grams of potassium hydroxide to achieve a concentration of 3%. The weight KOH was dissolved in a 100 millibeker, transferred into a 100 volumetric flask, and distilled water was added until the solution reached the mark. Then we need to homogenize it. This procedure is repeated to prepare another KOH solution concentration. After the carbonation process complete and we are ready to make an activator solution, the next step is the charcoal was ground and sieved using a screen with the size 80 to 100 mesh size to obtain a uniform particle size. And then the sieve charcoal was then soaked into COH solutions with the varying concentration, which are the 5%, 10%, 15%, and 20% for 24 hours. After soaking, the activated charcoal was filtered from the activator solution using Wattman number 42 filter paper and washed with distilled water until a neutral pH was reached, and the neutralized charcoal was then dried in an oven at 110 degrees Celsius for about 3 hours, followed by cooling in a desiccator for 15 minutes. At this point, an initial quality analysis was performed, including moisture content, ash content, volatile matter content, and iodine absorption capacity. And we already done do this research, and the next is the research results that will delivered by my partner, Andri Kurniawan.
Thank you very much, Gita. Now, let's move on to the research result. As you can see from the graphics, the moisture content analysis determines the percentage of water in activated carbon. The presence of water in activated carbon is related to the charcoal hygroscopic nature. This extremely hygroscopic feature is what makes activated carbon useful as an absorbent. The lower the water content, the less water remains to coat the pores of activated carbon. Now, let's have a look at the graphic. The moisture content testing in the graphic show a negative correlation between potassium hydroxide concentration and moisture content, where increasing the potassium hydroxide concentration from 3% to 20% progressively decreases the moisture content. The lowest moisture content was obtained at a concentration of 20% and the highest at 3%. This decrease is attributed to the hygroscopic nature of potassium hydroxide, which enhances its ability to bind water molecules from charcoal. Maximum water content reduction will support the physical activation process by maximizing water evaporation, which contributes to the formation of larger and more numerous pores. The total moisture content of the activated carbon produced in this study met the Indonesian national standard, which sets a maximum limit of 15%. Now, ash content analysis aims to identify the metal oxide content of charcoal, which is composed of minerals that do not evaporate during the charring process. A high ash content leads to poorer absorption capacity. Thus, efforts are made to keep the ash content as low as possible so that the absorption process can be optimized. As you can see here on the graphic, increasing the concentration of potassium hydroxide tends to decrease the ash content of activated charcoal. The decrease is observed from a concentration of 3% to the lowest ash content at a concentration of 10%. The reduction in ash content is attributed to the increasing capability of the potassium hydroxide activator to bind and dissolve metal oxides or mineral present in the activated carbon. However, there were fluctuations with a slight increase in ash content at 15% and 20%. This increase is indicated by the potential for the potassium hydroxide to be absorbed into the activated carbon and remain after the activation process, I should say. Despite the fluctuation, the total ash content produced in this study still meets the Indonesian industrial standard, which set a maximum limit of 10%. Now let's move on to the volatile matter. The purpose of analyzing the volatile matter content is to determine or identify the content of compounds that can vaporize at 950 degrees Celsius in activated carbon. During analysis, with heating above 900 degrees Celsius, nitrogen and sulfur will vaporize, and these components are what we call volatile matter. From the graphic, we can see that increasing the concentration of potassium hydroxide generally leads to a decrease in content of volatile matter. This decrease occurred at a concentration of 3%, reaching its lowest value at 10%. This is due to the function of the activator, which helps open the pores of the activated carbon, allowing the volatile substances trapped inside to be released to the maximum extent. A low volatile matter content is a direct indication of the increased absorption capacity of activated carbon. However, there is an increase in volatile matter content at a concentration of 15% and 20%. This increase is believed to be related to the high ash content at the concentration, which likely caused pore blockage and suboptimally hindered the release of fly ash. Nevertheless, the total amount of volatile matter produced in this study met the national Indonesian standard, which set a maximum limit of 25%. While iodine absorption analysis aims to determine the absorption capacity of activated carbon, One method which is used in analyzing absorption capacity is activated carbon toward iodine solution, the iodometric titration method. This absorption capacity can be demonstrated by the magnitude of the iodine number, which indicates how much the absorbent can absorb iodine. The higher the iodine number, the greater the absorption capacity of the absorbent. As we can see, a significant positive correlation between potassium hydroxide concentration and iodine number up to a certain point. Increasing the potassium hydroxide concentration from 3% to 10% increase iodine absorption capacity, which reached a maximum value of 812.05 milligram per gram at a potassium hydroxide concentration of 10%. This increase indicates that the optimal potassium hydroxide concentration successfully formed more macropores, thereby enhancing the activated carbon absorption ability. However, iodine absorption capacity then decreased at concentration of 15% and 20%. This decrease is caused by the potassium hydroxide concentration being too high, which triggers the formation of a crust on the surface of the charcoal, leading the pore blockage and reduced access for absorption. Based on this data, the activated charcoal produced at a concentration of 10% is the only one that meets the requirement of the Indonesian industrial standard, which is minimum of 750 milligram per gram. Guys, now the last one is the conclusion. It was demonstrated that activated carbon produced via chemical physical activation with 10% potassium hydroxide at 700 degrees Celsius meets the requirement of Indonesian Industrial Standard number 63730/1995. The key characteristics include a moisture content of 1.28%, ash content of 4.10%, volatile matter content of 7.78%, and a high iodine absorption capacity of 812.5 milligram per grams. So I think that's all from me. I would give it back to our partner, Mr. Wahyudi.
I think that is all from us. Thank you for your attention. Good morning and Assalamualaikum warahmatullahi wabarakatuh. Bye bye.